So passive transport sometimes requires the help of integral membrane proteins, like in the case of facilitated diffusion, but it can also be channel-mediated, which refers to a specific type of integral membrane protein known as a channel or an ion channel. On this slide here, we can really nicely see what an integral membrane protein actually is by looking at the ribbon diagram on the left-hand side. If you look closely, you can see how each piece of the protein comes together to form a pore. And that's essentially a tunnel through the plasma membrane. Now, ion channels have a lot of molecular similarities and homology because they're genetically encoded proteins. But there are subtle variations between them that give each channel unique properties. So, for example, channels can be different in terms of their selectivity. Some ion channels will only allow sodium molecules to enter their pore, whereas other ones allow potassium. Some channels are selective to more than one ion. So, for example, cation channels allow positively charged ions like sodium and potassium to enter the pore, but not negatively charged ions like chloride. Some channels are selective for monovalent ions and others for bivalent ions. So selectivity is important, and you get the idea. But one other important thing about ion channels is that in most cases, the pore is not open all the time. You can imagine that each ion channel essentially has a gate or a door that's protecting its pore. And there are a whole bunch of different ways that we can open it. That's known as the channel's gating mechanism. Now, some ion channels can open based upon changes in the charge environment across the plasma membrane. Those are known as voltage-gated channels, and we're going to talk a lot more about them in our membrane potential unit. Other channels are opened or closed when chemical messengers bind to the inside or the outside of the cell. And lastly, some ion channels can be opened based upon changes in the physical structure of the cell. And those are known as mechanically gated ion channels. Now, regardless of how we open or close the door, whether it's voltage gated, ligand gated, or mechanically gated, when the door is open, we can have tens of thousands of ions per second moving through that pore. And the two classification schemes don't have to be mutually exclusive. So you can have a voltage-gated sodium channel or a ligand-gated potassium channel. And so things can get pretty complicated. And because of that, people often assume that ion channels must be active transport. They must require energy investment. But they actually don't. Ion channels are always passive. Despite having really complex gating mechanisms and high specificity, at the end of the day, all they do is create a pore or a path for ions to move passively through the membrane. Now, we're going to talk a lot more about ion channels, probably more than you've ever wanted to talk about ion channels. But again, it happens for a reason. One of the really interesting things about this course to me is that we get a lot of opportunities to talk about diseases and the things that make us sick. And if you were to look at any disease that you're interested in, about 99% of the time, most likely 100, but I'm a cautious person, 99% of the time, you're going to find that there's an ion channel that's contributing in some way to that disease. And in fact, many diseases are caused by mutations in the genes that encode the ion channels. So there's this whole area of physiology that investigates these things called channelopathies. They're super cool. Anyone that's interested in any of this stuff can follow up by taking a course with Dr. Jingunis that specifically focuses on channelopathy.
Japan is crazy for fish. Each morning, thousands of merchants crowd Tsukuji Seafood Market in Tokyo. At Tsukuji, no product has a higher price than the one that's the most taboo, the puffer. It's the seafood version of Russian roulette, an extremely poisonous fish that the Japanese call fugu. Despite the danger, fugu appears on more than 80 menus in the Asakuso restaurant district. So ugly it's cute, the puffer doesn't fool most diners. Tom Caradana's in Tokyo for the full fugu experience, and he's brought his friend, Aki. Prudently, Tom has chosen to eat at Matsumoto. This 120-year-old fugu palace is known for careful preparation, important when you're dealing with a toxin 1,000 times stronger than cyanide.
I'd heard stories about people dying, of trying the fugu, but it hasn't really concerned me.
All the good humor in the world can't bury the risk. Over the years, hundreds of people have died from eating fugu. Chef Hayashi has Tom's life in his hands.
It'll be fine. Don't worry. I've been doing this for 53 years.
53年間やってま
I
す。
took the exam in 1949 and passed.
受験して1回目で合格した。
This is my Fugu chef license.
フルーツ免許証。
After World War II, fugu fatalities skyrocketed. Starving Japanese would comb restaurant trash bins. They'd salvage discarded fugu, grill the scraps, and die. So General MacArthur, who led the American occupation force, imposed strict controls. Fugu chefs had to get licenses. Even with stricter rules, death by fugu claimed 2,500 Japanese between 1945 and 1975. Regulation and education have cut the death toll to only 3 per year, but dozens of diners still get sick.
About 70% of the poisonings happen in private homes where people catch and prepare fugu on their own and get poisoned. That's most common.
At Tokyo University of Fisheries, Nagashima Tuji analyzes fugu poison. He hopes to develop an antitoxin for fugu.
So in addition to having channelopathies, ion channels can also be the target of toxins and pharmaceutical drugs. In the video that we just saw, we were talking about tetrodotoxin, which is a toxin that's evolved very specifically to inhibit voltage-gated sodium channels. But we've been able to take our knowledge of that drug and apply it to research, to study sodium channels, and even to develop new pharmaceutical drugs as well. So there is a little bit of a silver lining, and you'll be hearing about tetrodotoxin again later in the course. Now, because there's so much complexity in terms of passive transport, it's nice to see how everything we've talked about up to this point fits together. So here we're looking at a pancreatic beta cell, which is a hormone-secreting cell that's responsible for producing the hormone insulin. Now, insulin is released following a meal when the concentration of glucose in our blood is really high. And because the concentration of glucose in the blood is higher than that in the cytoplasm, we have a glucose transporter that allows glucose to enter the beta cell through facilitated diffusion. Once inside the beta cell, the cell can use the glucose like most cells do to produce ATP. But the ATP can then serve as an intracellular ligand for a potassium channel, which causes it to close. And when we close that ion channel, it creates a change in voltage across the membrane. So a nearby voltage-gated channel can open, and that allows calcium ions to come into the cell. And it's ultimately that calcium signal that leads to the release of insulin. So you don't have to know the details of this diagram, but I do think it's interesting to see how all of these different mechanisms that we've talked about up to this point are all interdependent.